Okay, so let's start with recalling what the big packing problem is. And again, the goal of today is to show you the different how to develop methodologically a random search algorithm to solve the bin packing problem and any problem that can be related to this type of bin packing problem. What do I mean by that? It means, I mean, application problem that you have seen in the exercises also that have presented in other lecture, for which there is a set of items, in this case denoted by I, with a set of elements, indexed by 1 to n, and then each item is assigned a weight. On the other side, there is a set of bin, in this case denoted by B, and each of these bin has a capacity, could be the same or could be different capacity for each bin. We have here different numbers, but basically this could be also the same number. So this, what do we want to do? We want to associate, we want to put items inside the bins, and we want to pack them inside the bin so that we can pack them as efficiently as possible within the capacity constraint. And our objective is to minimize the number of bins that we are using. So the objective function is the number of bins used, and the feasibility concept. What is the feasibility constraint? The feasibility constraints is the capacity constraints for each bin. So when two are the constraints that defines feasibility. One, that we need to pack every item. We cannot pack an item, we cannot leave an item outside of a bin. And also we need to respect to be within the capacity of each bin. We don't need to fill up the bin. We just need to find space for each item in the bins. Of course, a very simple solution to this problem is to put one item in each bin. So we have 10 items, we use 10 bins. We have 100 items, we use 100 bins. Of course, given that the weight of each item is less the capacity of each bin. Otherwise, if there is one item which doesn't fit in any of the bins, then we have what we call an instance, which is not feasible, because one of the constraints of this problem, which is to fit every single item in one bin, cannot be resolved, cannot be satisfied. Okay, so as you know, when we develop a random search algorithm, there are three basic things that we need to take care of. One is how we generate a random solution, so a general solution which has to be a possible solution. And then, given the solution, we need to check what the feasibility, how do we check feasibility for this problem. And then with each solution, there is an objective function value that we need to be able to compute. Let's focus on the first part. The generation of a random solution is deeply connected to the way we represent a solution. We have seen that for the knapsack problem, we have seen that several times. The knapsack problem requires a binary representation. At least we use a binary representation to denote whether an item is selected or not. For instead bin packing problem, what we use instead is what we call an integer representation. So we have an array of value. How many elements in this array? As many as are the items that we need to allocate. And then each position in this array corresponds to an item. And what the value in the position is the bin to which that item has been assigned. For example, we have 5 items, then the representation of the solution will be a vector with 5 elements. Position 1, position 2, position 3, position 4, position 5. Every position, each position represents one item, and the value inside that position represents the bin which is associated to the item in that position. For example, in this case, this solution is an integer array because it contains integer, And it is such that represents the solution of the following. Item 1, which corresponds to this position, is assigned to bin 1. Item 2, which is correspond to this position, is assigned again to bin 1. And item 3, 4, and 5 are all assigned to bin 2. So in this case, we have is this solution feasible? Is feasible? Why? Because we have 5 items and each item has been assigned to a bin. And then to check whether the other constraints is satisfied, we need to sum the item, the weight of the item which are associated to the same bin, and check whether the sum of the weights of this item is within the capacity of that bin. So in this case, we don't have the numbers in this specific example. I'll show you another example. But in this case, what we would need to do is to sum the weight of item 1, the weight of item 2, and check whether the sum of these weights is less the capacity of bin 1. And on the other side, we need to check the weight of item 3, of item 4, and of item 5, which are all associated to the same bin, which is bin 2. And once we compute the sum of these weights, we need to double check whether the sum of these weights is less the capacity of of the second bin. So in this case, all the items have been placed somewhere, and the sum of the weights of the item inside the bin is less the capacity of the bin, the solution will be feasible. The third thing that we need to compute is the objective function. In this case, for the basic, let's say basic bin packing problem, our objective function is the number of the bins that we want to use, and we want to minimize the number of bins used. So in this case, the number of bins are 2, which are exactly the different type of number that belongs to this representation in the array. Okay, now this is how we represent a solution. Now remember, we need to generate a solution. How we generate a solution for a bin packing problem? What we need to do it's a two-step procedure. We need to generate a random permutation of the items, and then given that permutation, we need to pack the item in that order using a defined rule that we could come up with whatever rule. I'll show you 4 rules. I already covered in the previous lecture class that I did on campus the first rule, but I'm gonna review this. Okay, so let's start with that. So we need to, this is our example instances. So we have 6 bins, we have 6 items, 1, 2, 3, 4, 5, and 6. And then each item has this weight, and we have a capacity of the bins, which is all the same. In this case is 10. So we want to pack these into the bins with capacity 10. So we need to generate a random solution. 2 steps: shuffle the item into a random order and place the item in a given order. I will cover this step later. For the moment, assume that we have shuffled in some way the items, and then given that permutation, we will need to apply a packing rule. Here are 4 possible packing rules. I'll focus in this recording on the next fit, and then in the additional recording, I will cover the other 3 rules. I want to outline one specific element here. So each of these packing rules, together with the permutation from which it starts, will generate a solution. We generate actually a random feasible solution. So there are 4 different ways of generating a random feasible solution. Each one is obtained applying one of these packing rules. What does it mean? What does it imply for us? Let's look for a moment back at the general framework of a random search algorithm. which is this one. So again, this is the general, and you see there are three main components here that we need to do: random solution, check feasibility, and compute the objective function. Here, what I'm covering now is simply this step. Each rule, each of the four packing rule will generate a different random solution. So once we change this step, we apply one specific rule, we have a random search algorithm. Then we apply the other rule, we have a different random search algorithm. So each rule will give life to a different random search algorithm for the same problem. Which is better? We don't know. Of course, you will see there are goods and bads, pros and cons for each of the packing rule. It's up to the decision maker. It's up to you to choose whatever you consider the best. But now, in this general pseudocode, what we are focusing is on this part. And let me go back to the rule now. So we are focusing on this. What is the next fit rule? So this next fit is starts with a given order of the items that we need to pack. And the main thing is, this is a very simple rule. Takes the first item and puts that in the bin which is open. So this rule opens one bin at a time. At the beginning, they are all closed. Then we open the first bin and we have the item which are processed in a given order, which is the permutation that we have generated. So takes the first item and check whether it fits in the open bin. If it fits, then it put that item in the bin and goes analyzing and goes on the other and the following item and check, is this item, does this item fit in the open bin? If it fits, it puts that in that open bin. Otherwise, it closes the current open bin, it opens a new one, and then puts this item in the other bins. Of course, what happens in this case, it happens that we may close a bin before it's fully before it's full. And also, had we chosen another item before, had we chosen a different order, maybe we could have filled it up the bins in a different way. And this is what makes each rule different. But again, let's look at the pseudocode for this and let's run it using the trace table. So this is not the random search algorithm. Again, this is the simple line, generate a feasible solution for a random feasible solution. So the input of this routine are two things, are few things. The permutation of the items, meaning we shuffle the item in some way, which is supposed to be given. I'll show you later how this is generated. Then the weights of the item and the capacity of the bins. And then it will return in output a random generation, a random solution, a random assignment of the items to the bin. So what we start with two parameters, two variables, the variable b and the variable rem. B is basically a variable that stores the label, stores the ID of the bin that is currently open. And this is instead is a variable which stores the residual capacity of the open bin. So at the beginning, we open the first bin and we have it's a full capacity because we haven't put anything in the bin. What happens later is we have a for loop that goes from that goes and explore the items in the permutation PK. So for each item, let's start with the first item. So this is a for loop which scans all the item in the permutation. So we start with the first item, k is equal to 1, and then we read the item which is in position k of the permutation, and then this is item I. What do we do with this item I? We check whether this item fits in the current bin. Remember, we have only one bin open and its capacity is, residual capacity is in this variable. So if the weight of the item is less than the residual capacity, it means that it can fit the current bin, and so we put the item in the bin. And we update the capacity. So the residual capacity was 10, for example. The weight of the item that we put into the bin was 5. So the new residual capacity is 10 minus 5, and this will be the new residual capacity. If the item doesn't fit in the current open bin, what happens? We open a new bin. So we update the value of this variable. So at the beginning was 1, and then eventually one item didn't fit, and then we need to open a new bin. So we open a new bin. Now the item will be the new bin, the new variable, the new value of B will be the new open bin. We initialize its capacity to full capacity, and then we put the item into this new bin, and we update the residual capacity of the new open bin. And that's it. We do this for all the items in this permutation. And so doing that for all the item in the permutation, it means that we are assigning every item because they are all scanned here. And since we are opening a new bin every time we need it, we are sure that every item fits in the every item is assigned to a bin, and the capacity of the bin is not exceeded. So this subroutine return a feasible solution. Why it is a random feasible solution? Because the permutation which takes as input is random. Let's look how this works using a trace table. So this is our instance. We have 6 items, and these are the corresponding weights. This is the capacity, and this after we shuffling, we obtain this order of the item. So this is the way we will be processing this item. At the first initial step, we have the first iteration, we have 0. So this is the initialization. Basically, we have B equal to 1. We have the residual capacity, which is equal to this guy here, and we don't have any decision. Here we'll keep track of different variables which are useful during the execution. And this is the actual solution that we are building. So let's start the first iteration. Remember, the first iteration, we will check and we'll scan the first item in the permutation. Then we will check its weight. If the weight fits the current open bin, we put the item in the bin. Otherwise, we open a new bin. Okay, so the first item in this permutation, so k is equal to 1. So we are going to look at the item in this permutation, which is item 2. And then this is the value. Pk is equal to 2, and the value, the current item is so item I, which is 2. Then we need to check the weight of item 2, which is wi. So item is 2, is this guy here, so which is 8. And then we ask ourselves, does it fit the current capacity of the current open bin? The open bin is bin 1, its current capacity is 10. 10 is greater than 8, so we can put the item in this bin. And so we put the item in this bin. This is the decision. We place the item in the bin. We update this guy. So putting the item in the bin means assigning the value of the bin on where we are placing the item to the position corresponding to the item. So in this case, this is our solution. Remember, the solution is an integer representation. So this means that the item in the second position, which is item 2, is assigned to bin 1. And then we go on. Go on means we increment k. K is equal to 2. The second element in the permutation P is 5, so we are analyzing item 5. The weight of item 5 is 1, 2, 3, 4, 5 is 4. We have 4 here. Is this item, does it fit in the current open bin? The open bin has a residual capacity of 2, so it doesn't fit in the current open bin. We need to open a new bin. This is the decision. We open a new bin, and so B is incremented by 1, and it becomes 2. Now we place the item into the bin. So we place item 5. You see in this position 1, 2, 3, 4, 5. We assign the item. We assign the bin where we are locating item 5, and then we update the residual capacity of the current open bin, which from 10, which was at the beginning, is now 6, because the current item that we have placed in that bin has weight 4. Now we look and we go to the next iteration. We are analyzing the third item in the bin, which is item 3, whose weight is 7. Here it is. Does it fit in the current open bin, which is 2? No, it doesn't fit. So we open a new bin, which is 3. We place the item in that bin. So item 3 goes in bin 3, and we update the residual capacity of the current, which becomes 10 minus 7, which is 3. We go on the next item, item 4, which is, position 4 in the permutation, which is item 6, whose weight is 1, 2, 3, 4, 5, 6 is 2. Does this fit in the current open bin whose residual capacity is 3? Yes, it fits. Then I place the item in the current bin, which is 3. And so item 6 is in position 3. And then I update the current capacity, which is becoming then 3 minus 2 is equal to 1. And I scan the next item, which is the next position in the permutation, which is now position 5, which is item 4, whose weight is 6, which doesn't fit in the current capacity of the bin. So I need to open a new bin, which is now bin 4. I place the item 4 in bin 4. Again, here you are here, and I update the capacity of the bin, which is 10 minus 6, which is 4. And here the last item. So we are in position 6 of the permutation. So we are looking at this item 1, whose weight is 9. Here you are. It doesn't fit in the current bin, so we need to open a new bin, which is now bin 5. We position item 1 in bin 5. This is the positioning, and then we are done. And the solution is now this. So item 2 is in bin 1. Here you are. In bin 2 there is only one item, which is item number 5. In bin 3 there are this item and this item 3 and 6. In bin 4 there is only item 4, and in bin 5 there is only item 1. So this solution is feasible. Every item is placed in a bin. Every bin is not overloaded, so all the items in the bins respect the capacity of the bin. And the objective solution, the objective function, the value of the objective function for this solution is the number of open bin, which is 5. So once we have this, we have a feasible solution. Now, in the next recording, I'll show you the next packing rule.